density. What is density? Actually, it's a little bit more complicated than that. But yes, in this case, we're going to talk about mass over volume. Density is pretty much any stuff divided by spatial dimension. Okay, so you can have linear density, where you divide mass by length. Right? That's a density. It's not the density that you were taught in high school, but it is a density. Okay? You can have area density, which is mass divided by area. Yeah, area. That's usually and it could be charge density, right? In
Physics 202.
we're going to spend a lot of time talking about charge densities. It's total charge divided by length, or total charge divided by volume. Okay, so you want to be very specific when you're talking about density now, because we have different kinds of density. All right, but let's start with the most basic one. Density, which is denoted by this squiggly P. What is the name of this P? Rho. Rho. This is a Greek. So in case you haven't joined some sort of fraternity or sorority and you're not familiar, or you're not Greek, this is the Greek alphabet. We basically don't. How many letters are in the English alphabet? 26, right? Some of them look similar. Upper and lowercase. Okay, so that maybe gives you like twice 26. So we added more letters, and we still reuse letters all the time because we like to confuse introductory physics students. So, and you'll notice that like there's some, depending on what field you work in, people have their favorite way of describing variables. Like engineers use different variables than physicists for the same things. For instance, electrical engineers, they have an I and J issue. So what do they call, current's always I, right? They also deal with imaginary numbers because they do this thing called Fourier stuff. So what do they use for imaginary numbers? J. So an imaginary number in math and in physics is always I. But in electrical engineering, often they call it J. Why would you want to call it J? So you don't get confused with current and ruin your problem. Okay, so there's a lot of practical, it's annoying the way that we define variables, but there's usually a reason. Sometimes the reason is we've done that for the last 100 years because somebody decided to do it in a published paper and no one's ever fixed it because we just haven't gotten around to it. Because there's no like greater body of physics that controls the variables. It's just kind of random. So, sorry, but get used to it. The other thing, so this is rho. Pressure is P. They often appear in the same equations. Try not to screw it up. Also, this rho, mass over volume, is for mass density. We also use rho for charge density. So depending on what kind of problem you're doing, just be careful. So this is mass, this is volume, that is density. Okay? And this usually is related to, I mean, at a very fundamental level, what atoms things are made of. Okay? So for instance, Red Bull has a particular density. It's probably about the density of water. Okay? If I pour half of this Red Bull into a cup, and let's say most of it's still in the can. So we have a small amount in the cup, a large amount in the can. Which one has a higher density? It's exactly the same. So when you take a material and you cut it into pieces, the total mass changes, the density does not. Density is generally a material property. Same with charge density, unless it's a conductor, then things get weird. Okay? So here's some standard densities in kilograms per meter cubed. You'll notice water has a really nice density. It's about 1,000 kilograms per meter cubed, which if you do the unit conversion, it's a gram per centimeter cubed. 1 gram per centimeter cubed. Water is the easiest one to remember. All these other ones, less easy to remember. You can see some things are more dense than others. Lead, pretty dense, but not as dense as platinum. Okay. But when we want weights, we usually use lead, even though it's not as dense as platinum. Why?
It's less expensive.
Yeah, it's a lot less expensive. Lead is cheap, don't eat it though. And platinum, not so much. Okay. Also, fun fact, platinum's really pretty, but It's not a good thing to use for jewelry because the saws and the ER can't cut through it. Gold, nice and soft. So when you're buying rings, if you decide to get platinum because it doesn't get damaged as easily as gold, just keep in mind you may be making a choice to not keep your finger. Yeah. Fun medical facts. Okay, let's try a problem. Okay, so we're about 50-50 on aluminum or iron. There's a couple, somebody put E. They really bought into the idea that you don't have to be right. You are getting credit, person who put E. All right, so discuss this. We'll take about a minute and a half, and for people. Better. Okay. The answer is aluminum. Now, why?
It's less dense, 84.
Yeah, aluminum is less dense. That means you're going to need more of it to get to the same mass, okay? Let's say you want a kilogram of rocks. How much, let's say you have this many rocks, okay? Like this size, a rock this size. If you want something that weighs the same in feathers, you're going to need more or less feathers? More. You're going to need I think this is a technical term, a crap ton of feathers to equal a rock this size, okay? So less dense things, you need more of them to get the same mass, okay? You need a larger volume for the same, that's how density works. All right, so just for clarity, because this is, you guys aren't used to the system of this class, the way these are set up, there's sort of like a visual code to how these slides work. So you'll see if we go back to the last slide, it has this A, B, C, D, and it says clicker. So that means clicker, okay? These other problems, you'll see they're on graph paper to indicate, write this. And there's two types. There's examples, which are, it'll say example 1, and it'll be in blue. And those are ones that I do, and you guys can follow along. And then there's problems, and those are the ones that you guys do. I'd like you to try them. We usually take 5 or 10 minutes. But I don't know if you guys noticed, but on Canvas, all these slides are posted, right? The notes are all posted ahead of the class. So basically all these slides, but without the animations and without the solutions. Okay, so if you don't need to necessarily spend time writing down what the problem is, because you can access that in a PDF form. If you want to, you can, but you only have like 5 or 10 minutes to write, so it's a good time to practice solving problems. Now, at the end of the time that you guys work on it, I'll go over it, but I highly recommend don't just wait for me to go over it. You'll find, even if you just struggle and you don't get far on the problem, when I do the answer, you'll remember it better, because it'll be linked to a feeling of personal failure, okay, which is a very strong memory. So it helps you. Failure is the best way to learn. I guarantee you remember problems you got wrong a lot better than the problems you got right, okay? So please, please, please use this time to practice doing the problems. It will feel painful, but it's better to feel like you're frustrated now than during an exam. Oh, cool. All right. Welcome to the new technology, guys. So we have a solid cube of aluminum. It has a density of 2.70 grams per centimeter cubed. It has a volume of about 0.2 centimeters cubed. And it's known that 27 grams of aluminum contains something like 6.02 times 10 to the 23rd atoms, which is a number that might seem somewhat familiar to you from probably chemistry. How many aluminum atoms are contained in the cube? So this includes density, but it's primarily a unit analysis problem, right? So where should we start? What things do we know?
The density.
So yeah, let's start with the things we're given. I'll highlight them. Okay, let's see. We have density, right? We have a volume, and we have
a mass, and then we have this other thing, which is atoms. So those are all the numbers that we're working with, okay? We also have a formula, an equation. What is it? Yeah, density, right? So we know that rho is equal to mass over volume, okay? But we're given density and volume, so we probably want to rewrite this in terms of what we're solving for. So we want to know the mass. So that means we just do some algebra, and now we have mass is equal to rho v, okay? We can plug this in. So that means since we know that mass is equal to rho times v, we know that density is 2.7 grams per centimeter cubed. And we know that our volume is 0.200 centimeter cubed. So one question, why did we not convert to meters? It's going to cancel. Yeah, because we can see that it's going to cancel, right? If everything's in centimeters and we're not getting an answer in centimeters, if it cancels, that's fine. So we'll cancel it, right? And that means we end up with a mass. And what's the unit of our mass going to be in? Grams, right? Because we canceled the centimeters. So we end up with 0.540 grams. Okay, oh, this had a 0 on it. Now, why do we have 3 sig figs? We're doing a lot of things right here. The precision level, because both of the things we multiplied had 3 sig figs, so we kept the 3 sig figs. We keep the minimum number. If one of them had 3 and one of them had 2, how many would we keep? 2. Okay, so now we know the mass. All right, we want to know how many aluminum atoms are contained in a cube. So we know that, let's see, volume. Yeah, so we know that there's, let's see, a mass of the sample, right? And we know that that should be equal to some constant, okay, something, and then that's the number of atoms in the sample. There's other ways to do this, but we're going to do it this way. We also know that for aluminum, so we have a mass of 27 kilograms. That's equal to some constant times N for 27 kilograms, right? Oh, grams. Sorry, it's grams. Yes.
Can you make it a little bit bigger, please?
Possibly. Let's find out. Can I even figure out where my mouse is? It maybe. Hey, that looks good. I'm not sure that's actually bigger. It just has bigger margins. That's weird. All right, I'm gonna try to make it take up the whole screen. Is it actually bigger? Okay, good. Cool. All right, so we can divide these. This is just a ratio, okay? What does this K mean? Yeah, it's a constant. It just means that we know this is proportional to that, okay? You can also write it as like mass sample is approximately or proportional to N sample, right? Basic idea, okay. But yeah, either way. The nice thing about this is then we can cancel out the K's. They should be the same, right? It has the same proportionality. That gives us something that looks like mass of your sample is equal to N of your sample, mass of 27 grams is equal to, oops, not equal, there we go, over N of 27 grams. So all we've done is we made a ratio of these things. There's other ways you could do it. You can solve it algebraically and plug it in. That works too, okay? The basic idea is that you solve this for N of your sample, and that's going to be mass of your sample times N for 27 grams over mass of 27 grams. You plug in your numbers, so that gives you 0.540 grams, 6 times 10 to the 23, oh, I need a 6.02. 6.02 times 10 to the 23 atoms per gram, right? All over 20 27.0 grams. You plug all that into a calculator, and that should give you 1.2 times 10 to the 22 atoms. Okay, the only other thing to keep track of here is, once again, we are canceling grams, and that's why we end up with atoms.